Hi, and welcome back to Codex. Our speaker today is Demetrio Labate from the University of Houston. Professor Labate is an expert in applied harmonic analysis. Today, he'll tell us about function approximation with neural networks. Take it away, Demetrio.
All right, thank you, Emily. Good day, everyone. So the talk today is actually a joint work with my doctoral student, Ji Shi. It is, as Emily mentioned, a talk about using a neural network for functional approximations, in fact, multivariate approximations. And it falls into a class of, studies that appear recently in literature, that essentially want to set up theoretical foundations, a theoretical foundation for, the expressive power of neural networks. So a few words, everybody knows neural networks are everywhere in applications, and the property that, in a way, explains their success has to do with the ability to deal with high-dimensional data. And so it is a natural question to ask, how is it that they are so efficient in dealing with these high-dimensional problems? And so in my talk, I will essentially have two main blocks. I have some background material where I will set up notations and definition about neural networks. Then I will review some results, in part classical, in part more recent, about approximation properties using neural networks, including deep neural networks. And then it will be the main part of my talk, which is about applying deep neural network for functional approximations and dimensionality reduction. In fact, I will work with functions that are defined, supported on manifolds. And that will be essentially the main content, the main new component of my talk. So let me start with some background. And a neural network is essentially an algorithmic pipeline that processes an input in RD. I will denote with capital D the input dimension. This will also be the ambient dimension. And we return an output in RK. In most cases, I will deal with actually output in R. And so the way this algorithm works is essentially alternating between two very simple operations. One is actually the affine linear transformation mapping an input X to AX plus B. And I will denote this operation with this W. And then a nonlinear activation function rho that acts component-wise. And so the neural network alternates between these two components. The key observation is that unlike, some of the traditional algorithms that apply for processing data, where the key operation is actually linear superposition, in the case of neural network, the main difference is actually that the key operation is functional composition, which endows this type of method with some particular properties, right? And so, again, let me reformulate the same idea here by presenting the neural network as this sort of iterative process that takes an input X and then repeat multiple times this operation of computing intermediate values, right, of the variable that I denote with X tilde L by first applying the affine transformation W and then the R, the rho. This is repeated L times until you get an output that I denote with XL. So in this formulation here, you see that the user has an input, an output, right? And there are some intermediate values, L minus one intermediate value, that are normally called the hidden layers or hidden variables of the neural network. Now, as you know, in practical applications, the matrices and biases that are present in this algorithm are learned during an appropriate training process, but in this talk, I will ignore the training. For me, the neural network is just a forward processing machine, right? I will ignore the training. I'm only looking at neural network as, in fact, as you will see, a structured parametric class of functions where this parameter can take some values, and I will ignore the process by which these values are going to be computed. Now, the simple situation is the situation where there is a single hidden layer. In this case, you're dealing with the so-called shallow neural network. In this case, you can express the output of this operation, which is, as you see, the application of a affine transformation, followed by linear activation, followed again by another linear operation. So at when you write this explicitly, you see that in the case of a shallow neural network, the function that describes the output is here nothing else than a superposition of activated affine functions. You have multiple affine function. Actually, number n is associated with the number of units or neurons, and those are in fact then composed with the nonlinearity, generating this special type of linear decomposition. In the case of a deep neural network, you have multiple hidden layers, so you may end up with an expression of this form. Here in this example, I show the analytic representation of a neural network with 4 layers, in this case, 3 hidden layers and 4 layers in total, because I count the output as an additional layer. And of course, for this expression to make sense mathematically, you need to make sure that the dimensions of the matrices and vectors B are matched. I will leave this, undetailed. So there is, of course, a graphical representation of a neural network that, makes this operation describe them graphically. Here you see the same 4-layer neural network described, in the special case where the input has dimension 2, the output has dimension 1, and you see therefore that there are 3 hidden layers, and the input is being mapped to the output through this operation, right? So in general, if you're dealing with multi-layer neural network, you can think of the function being generated as part of a special class of function that I call that, in fact, is a parametric family of function structure, in the sense that, they have a special form, and in the notation that I define below, I will denote with A and B the, matrices and biases of the affine transformation. W will denote the entire affine transformation. A are the filters, B are the biases, rho are the activation functions. I will count with this. I will count with L the number of layers, with N the width of a layer, and N of phi will denote the total number of neurons or units, adding up, the elements present in each layer. And with the parameter M, I will denote the number of non-zero weights or parameter. This number M is particularly important because it counts, in a way, the number of coefficients, in a way, the complexity of the information that can be carried out through this parametric family of functions, through the specific realization of the function set. So, of course, the same notation as a graphical representation. Here in this example, I show, for example, that in this special 4-layer network, I can count the number of layers, the number of neurons, and the number of weights, right, consistently with the notation. I mentioned the activation function. Of course, there are many choices for many possible selections for the activation function. This is a nonlinear function. Some of the most common are the sigmoid, which is continuous, and the differentiable, and the ReLU, the rectified linear unit, display here. And as you know, the ReLU is the most common activation function in deep neural network. In fact, the popularity of ReLU emerged, with the emergence of CNNs due to practical consideration, in part simplicity, in part, properties of the training process, right? But the ReLU is very common in deep neural network. And in fact, the theory that I will discuss for the second part of my talk is specific for deep neural network with ReLU activation function. As I will say at the very end, the approximation properties are very different if you replace the ReLU with something else. Anyway, in this talk, I will identify neural network with functions, even though, there may be a distinction between the graphical representation and the function. To me, a neural network is identified with a function, right? And so I will, therefore, introduce a notation for a specific function class for a tuple M0, L0, B0, where M0, L0 are extended natural numbers, B is positive. I will describe with the symbol script F, M0, L0, B0, the function class of neural networks for which the number of layers is bounded by L0, the number of weights or parameter by M0, and the scale, the maximum value of overall parameter is bounded by B0, right? So this is actually this function class associated with neural networks. All right. And so now I can move to the second part of the talk, which is a review of existing results about approximations using neural networks. And so since the 80s, people have been looking more carefully into what type of approximation property you can associate to this type of algorithmic constructions. And here is one elementary construction that shows, in fact, in a way which is quite natural to analyze approximation property with neural networks. So let us consider a function, univariate function, which is Lipschitz with constant b. And then this proposition states that given any epsilon positive, you can approximate any function f in this class uniformly using a shallow neural network where the nonlinearity is just the threshold function. What you find in this case is actually that the parametrization of the network has a number of parameters of the order of 1 over epsilon, right? So as clearly as you want to improve the accuracy, the number of weights grows as 1 over epsilon. And the argument to the proof, I will just quickly go over, is quite simple. It just starts by partitioning the domain of the function into m subintervals, and then you can essentially approximate your function with piecewise constant function, and this piecewise constant function is identified with a shallow neural network, and then you can show that this construction will lead, in fact, to a uniform approximation where, as I anticipated in the statement, the accuracy epsilon is tied to the number of partitions and therefore the parameter you need to achieve this type of approximation. So a similar result extends to the multivariate case. If you want to generate a similar approximation using neural network with ReLU, here I mention a result that is somewhat the closest to the 1D case. Here you need to use, in fact, more than one hidden layer, but the result you get is very similar. So you can approximate a function with neural network, with, in this case, ReLU activation function. What happens in this case is actually that the number of parameters that you need becomes epsilon to the minus d. So if d is the input dimension, then the number of parameters will grow now exponentially with the dimension. And so this statement identifies what I will become a theme in the next slides, which is the fact that the number of parameters, of course, grows exponentially with d, and this is a manifestation of the so-called curse of dimensionality, right? All right. Now, more generally, people have developed a class of approximation results that go under the name of universal approximation theorems. Let me quickly go over this type of results. So in this terminology, we say that a class of functions, and I denote it with the symbol calligraphic F, is a universal approximator over a compact set if for every continuous function g and target accuracy epsilon, there exists a function f in this class that approximates uniformly, right, the target function. And first of all, in this definition, one needs to assume compactness. Otherwise, it easily build counterexamples showing that it is essentially impossible to build universal approximators. The other point I want to make is actually that without loss of generality, we can assume the compact set to be the interval 0, 1 to the d. And finally, that, of course, we are already familiar with examples of universal approximator. For example, the Weierstrass theorem states that polynomials are universal approximators over a compact set. And now the universal approximation theorem, which are actually quite popular in the literature of neural networks, states that that shallow neural networks are in fact universal approximators. In particular, the result that I stated here, the first one by Hornig in 91, says actually this is true provided the activation function is C infinity, non-polynomial. And Pincus, in fact, remarked in another result. And in fact, this is a if and only if condition, right? This is what you need, right? Is not only sufficient, but also necessary. But anyway, shallow neural networks are universal approximators over, here I state 0, 1 to the d. Okay, so, oops, oh, sorry. Now, in these statements, if one goes and checks the argument, it turns out, not surprisingly, that in order to achieve arbitrary accuracy, then the number of weights, in this case, the number of units or neurons in the hidden layer need to become arbitrarily large, as you let the accuracy become arbitrarily fine. Okay, anyway, so therefore, to summarize where we are so far, shallow neural networks are universal approximators, which is something that we already know to be true, for polynomials. So the question is, okay, so why do we really care about having neural networks? And also, if shallow neural networks, in fact, achieve this type of approximation, why do we need to go deeper? And somewhat this will be related and this to the issue of computational complexity. So having, as we know, approximation property is not sufficiently useful if it's not combined, or associated with, beneficial or useful computational property, right? All right. So here is the kind of the more general result, right, that I want to state. So the first observation I want to make here is actually that shallow neural networks are in fact comparable to the traditional approximation method in terms of computational complexity. So similar to what I stated before, right? For function f which are continuous in 0, 1 to the d, then the result by Mashkar in 96 shows that you can approximate uniformly functions in this class with a shallow neural network, right? Provided the number of parameters is of the order of epsilon to the minus d, right? So this result is the complexity associated with this approximation method is in fact identical to the one you will get with a traditional approximation method. So can we improve properties by going deeper, right? And so next section is actually the role of that in a deep neural network. Let me review, right, what is known so far. So there are in fact a dual version of the approximation theorems that to the one that I stated before, showing that you can achieve also uniform approximation properties using deep neural networks. In this case, you don't need to make the network arbitrarily wide if you trade off width for depth, right? And so this result by Kidger and Lyon shows that, in fact, you can provide uniform approximation to functioning which are continuous in 0, 1 to dd, while keeping the neural network, in a way to control the width, right? In this case, controlling with the input dimension d, essentially. But what you need to pay in this case is actually that the network will have to become deeper, right? So you can make it deeper rather than making wider. In practice, in practical application, it is nowadays, most application, in fact, exploit that for several type of goals, including the idea of, in fact, achieving better approximation properties. And the reason for using deep neural network is the ability to, in fact, exploit functional composition, which is, the property that I stated at the very beginning. And there is this heuristic observation, mostly heuristic, as I will show, that going deeper rather than allows you to improve expressive power in a certain sense, right? So here is one point of view that somewhat will suggest the advantage of functional composition. So let me look at an example of piecewise linear functions on R, the simple triangle function stated there and illustrated below. So the triangle function that I describe here is easily implemented through a shallow neural network with the ReLU activation function. So you see in this case, my phi is the composition of, is the application of an affine transformation combined with the ReLU multiplied by another linear transformation. And so this will implement exactly this triangle function, showing that I achieve, in fact, I build this type of piecewise linear function by using, in this case, a shallow neural network with two units in the hidden layer. More generally, right, I mean, it is true, in fact, that with the same idea, I can represent any piecewise linear function with at most two breakpoints using two units, right, in my hidden layer. Extending this idea or generalizing, I can in fact show that if I replace my two units or two neurons with n, I can in fact describe piecewise linear function with at most n breakpoints. Now, so far, what I found, in fact, is actually the neural network is equivalent in a way to classical representation methods, because I have an expressive, anyway, my neural network in this case has n squared parameters and is describing, n breakpoints, which are in fact contain exactly information associated with n squared. So the interesting observation is actually if I build a multi-layer neural network by composing these layers, right? Now the number of breakpoints is increasing exponentially because every time it doubles, right? While the complexity of the network is of the order is increasing like n squared. So this suggests, in fact, that by composition I can increase complexity in a way which is a little more sophisticated than would you be able to do with classical representation methods. And this is in fact part of the intuitive version of a group of results recently developed by papers that involve Divot, Ranin, Petrova, Foucault, and Dobeshi, showing that deep neural network exploiting compositionality can in fact improve approximation results for some type of function classes. Now, there are some results showing provable advantages of deeper architecture. So, for example, Tergalski has some example where he shows that there are deep neural architectures that achieve approximation properties that cannot be achieved by any shallow neural network unless the number of nodes is growing exponentially. So there are provable results showing that going deeper you improve approximation properties. Nonetheless, none of these results, as far as I know, really show that just by virtue of building deeper architecture, you can avoid this scaling with D and avoid the curse of dimensionality. In fact, in a sense, the best achievable result from this point of view is the one that I state here, is the theorem by Shen, Yang, and Zhang, 2022, showing that for functions which are Hoelder continuous with smoothness alpha, when the Hoelder constant is bounded by lambda, I can use deep neural network with ReLU activation function to provide uniform approximation. And in this case, the result shows that the complexity neural network, in fact, should be of the order epsilon to the minus d over alpha, so still grows in a way which manifests the cursor dimension. And this result is, in fact, should achieve the optimal decay rate in an appropriate sense, right? So the conclusion at this point is, yes, the depth offers some advantages, but the kind of complexity that you need to achieve in this case is still, explicit dependence on the dimension. All right, so to achieve dimensionality reduction, the point of view that we need to introduce is, that I will introduce is somewhat consistent with the point of view of manifold learning. And let me start with this first observation that anyway, so I started by remarking that deep neural networks in applications have shown heuristically, right, they can in fact overcome the cursor dimension in many cases, right? However, this, as we said, cannot be fully explained just by looking at the direct approximation properties as presented so far. So the cursor dimension, as I reported, is in this phenomenon by which approximation method deteriorate exponentially fast when the dimension d increases, and this is something which is quite known in numerical applications, including solvers for PDE, where you find this phenomenon of the accuracy. So the number of parameters needed to achieve some epsilon accuracy to grow with a rate of the order epsilon to the minus d, right? This is this typical case. Now, it is also true, and this is what people typically invoke in the area of manifold learning, that high-dimensional data using many applications exhibit a low intrinsic dimension. And I will exemplify this with some classical examples. So there are classical data sets like MNIST, right? Consisting of images of size 28 by 28, leading to data that live in this space of dimension 784. As you see, these data, of course, are highly structured. And one can show with appropriate arguments that the true dimensionality of this data set is, in fact, of order between 8 and 13. And similarly, if you look at more complex image data sets like ImageNet, in this case, you are dealing with images which are RGB of size 224 by 224. So each image lives in a space of dimension about 150,000. Also, in this case, there are measurements that somewhat suggest that the true dimension is between 26 and 43. Now, here I'm being a little vague about what I mean by intrinsic dimension. This can be defined in a more rigorous way. I'm not going to do that. But the point I want to assume is the so-called point of view of manifold learning or the manifold hypothesis. As I say, this is frequently invoked, either explicitly or implicitly, to explain why high-dimensional data may have some low-dimensional description. And the manifold hypothesis will state essentially that the d-dimensional data, capital D dimension, is in fact embedded in a lower dimensional manifold, where this low dimension is much lower than capital D, right? And so this is suggested by the picture, showing that perhaps what happens for the MNIST data set is actually that my written digits are in fact contained not into this space of dimension 764, but in a lower dimensional manifold. So the point of view I will adopt is the point of view by which the function that I want to approximate is embedded in a space of dimension capital D, but in fact, I will try to approximate the function in the manifold where it is in fact supported. And so rather than try to approximate my function f in RD capital D, under the assumption that the function is defined over a lower dimensional manifold, I will try to discover the approximation in the lower dimensional setting, right? So the idea underlying what I'm saying here is actually that if you do that through a neural network will somewhat discover the coordinate transformation. So a neural network, by the training, will learn this lower dimensional representation. And this is not an effort that I will need to carry out explicitly, right? So for my analysis, I will work with Hoelder continuous functions with domain in the manifold. My manifold will be a smooth, the manifold will be a smooth, compact, d-dimensional manifold, where d little d is significantly lower than capital D. And so it is possible to define a norm, right, in this, an appropriate norm, of course, in the Hoelder space, and to define properly Hoelder space functions with support in this smooth manifold. Now, a very seminal and influential result in this area was a paper by Shaham, Cloninger, and Koifa in 2018. And in fact, the title of my talk is an intentional reference to that paper. The title of the paper was something about provable approximations of neural networks. So my title is a reference to their title. And I mentioned here, following their name, some other papers. There have been more, that have been extending, improving the result. So the informal version of their paper is the following. Let calligraphic M be a smooth, compact, d-dimensional manifold. So the manifold is d-dimensional, little d, but it is embedded in this capital D-dimensional space. And I'm considering functions which are Hoelder continuous with smoothness alpha in 0, 1, with Hoelder constant bounded by lambda. And the theorem states that I can, in fact, approximate this class of functions with deep neural networks having ReLU activation. And I can do that satisfying this estimate, which states that, in fact, the complexity of the neural network, the number of parameters, scales with epsilon to the minus d over alpha, where d is the dimension of the manifold, not the dimension of the ambient space. So essentially, what they say is the complexity of the neural network that required to approximate f will depend only weakly on the ambient dimension, because it still appears in the constant, multiplicative constant. But other than that, the dimension of the parameterization will scale with little d, right? So this is the key observation that has been, proved in several versions of this theorem. I mean, here I'm presenting an informal version because the complete version will include more technical assumption about the manifold and the way you control it. But the key point is that you can scale it with little d rather than capital D. The dimension d still contain in a weaker form into the multiplicative constant. If I remember correctly, the original theorem by Shahan, Cronje, Koifam did not compute the explicit dependence, but other papers found that the dependence on D is of polynomial type. So what is the argument behind the theorem? Let me just sketch in one page what is the idea of the proof, right? So the key idea, their idea is to start by constructing a basis. In this case, they selected a wavelet frame for the ambient space, and they construct this frame, right, using, in fact, ReLU neural network. And then they build an atlas mapping the, so they build an atlas covering the manifold with open balls and defining maps, charts into the lower dimensional space. Now they use this, the open cover, they partition the manifold, right, in such a way that they can represent function the manifold as sum of functions in Rd little d, and they can extend the wavelet frame from the original domain on little d to capital D. And by doing that, of course, they need to take track of the geometry of the manifold. This is essentially the idea, right? So their argument is essentially constructive. And of course, the technical difficulties here are in fact in controlling the combination of different charts so that you can in fact control the dimension. So the result that I present here, right, is actually improving in a way the type of estimate by addressing the issue of the dependence of the approximation, right? The depend on the capital D in the constant, right? So the result that I present here is also stated in an informal form, is that, again, I'm considering a compact Riemannian d-dimensional manifold little d embedded in a capital D-dimensional space, right? And again, I'm looking at functions which are Hoelder continuous on the manifold with within a ball, right? So with Hoelder constant bounded by lambda. Now, I can compute a d sub e. Here, d sub e is for effective dimension, which is a dimension between little d and capital D. And this d is defined explicitly such that I can approximate any function f in the Hoelder class with a deep neural network with ReLU activation function, satisfying this type of estimate. Now, what happens in this case is actually similar to the theorem before, right? Also in my case, the parametrization neural network M scales with epsilon to the minus d over alpha. So the exponential part, right, scales with the, not with capital D, not with the ambient dimension, but with my effective dimension dE, which is not dependent on capital D, but only on, anyway, so which is smaller. But the additional part is actually my multiplicative constant is also independent on capital D. So in this case, I can completely avoid the dependence on capital D. Here, just a warning that my M in this case is not the total number of parameters, but it's the total number of parameters in the hidden layers. If you think, of course, I cannot avoid the dependence on capital D in the input layer, right? The input layer, of course, will have to map the input into the network, so there is a dependence on capital D there, which is unavoidable. I can only avoid the dependence in the remaining part of the network, right? Essentially the part that I can design, right? So this is the main difference, and in a way the improvement, that the network complexity grows with, again, with epsilon to the minus d over alpha, but the constant now is independent on capital D. Right, now, in order to prove this type of result, the one key difference actually is that rather than using a constructive argument to establish the low-dimensional mapping, right, I'm going to, in fact, use a version of the Johnson-Liljestrauss lemma that establishes a low distortion embedding from a high to a low-dimensional space. So this is the classical statement in RD from 1984. The Johnson-Liljestrauss lemma states that given a delta in 0, 1 and p points in RD, capital D, I can find a lower dimensional space where M depends on the number of points and on delta, so that there is a Lipschitz map from RD to Rm, which is almost isometric, right? So you see that the distances between the F and the X are almost the same up to this distortion factor controlled by delta. So he states that there is this low distortion embedding with a trade-off between isometry and dimensionality reduction. People who are familiar with the RIP may know that there is a connection between this type of property and the RIP. And I also want to mention that the relevance of this type of lemma in the context of neural network has been already noticed by other authors that I mentioned here. Now, for my result, I will in fact apply an extension of this lemma to the manifold setting. And the result that we use is based on this theorem by F. Teccari and Waking. This is a version of the Johnson-Liljestrauss lemma on manifolds, valid for, in fact, compact Riemannian submanifold of RD. Here there are some technical assumptions, which are the same assumption that we need to assume in our result. So here we need to have something called the condition number to be bounded and the volume satisfying some condition. Under this assumption, then this version of the Johnson-Liljestrauss lemma states that on manifolds, right, you can define an ortho projection from capital D to D delta. So you see there is a family of dimensions, right, that are less than capital D, such that, you know, with high probability, you can achieve almost isometry, right? So let me comment about the technical requirements. Here there are some requirements, which are the condition number, the construction of this ortho projection. So the condition number 1 over tau is technically defined as the norm of the second fundamental form of the manifold. This is related to tau, which is the reach. And the reach is measuring the essentially the smallest distance, right? So is the largest number such at any point at a distance less than tau from the manifold as a unique nearest point on the manifold. So it's measuring, in a way, the smallest width, right, inside the manifold. So what are the implications is actually that having a bounded condition number implies in practice that the manifold cannot curve too much. So not surprisingly, there is a connection between the condition number and the curvature. And related to that, in fact, angles between tangent spaces and nearby points cannot be too large, which is leading also to the fact that geodesic and ambient distances are not too different, right? This is what happens in this case. And then, in the construction, of course, there are these random ortho projections, which are mapping the capital D dimensional space into this lower dimensional embedding, which is not little d, but d delta. There is somewhat you need to make this space a little, you need to increase the dimension in a way dependent on this delta, which is the distortion parameter. So in the lemma, delta is a parameter ranging between 0 and 1/3, right? And in practice, what does it mean is actually the delta is controlling the trade-off between isometry and dimensionality reduction. So as delta is closer to 1/3, right, you weaken the isometry, but d delta become closer to d, and as delta is closer to 0, you have better isometric property, but you're farther away from capital D, so you may lose in dimensionality reduction. So for us, having being close to little d is prominent, right? So we choose delta to be 1/3 in our final state, right? And so what is the idea of our argument? Let me go over this idea in a few slides. So we start from my function f, which is in this Hoelder class, right? Within a bounded ball. And so we want to define we will start by constructing a lower dimensional function by applying the Johnson-Lindstein's lemma, by applying, in fact, a random ortho projection. This will be the first step of the proof, right? Now, once we define this lower dimensional function, then we need to make sure that the function we construct share the regularity properties of the original function, right? This is not immediate. And once you build that lower dimensional function, which is also Hoelder continuous, then you want to construct a neural network where you control, in a way, the parametrization wisely. And finally, you want to go back from the network approximating the function, the lower dimensional space, to the network that approximate, in fact, the original net, right? The difficulties in carrying out this program is first to control the regularity of the projected function, and then, of course, to build appropriate neural network, ReLU neural network, with a parametrization which is somewhat controlled, right? And so let me mention some of the steps here, right? So the first part of the proof is, in fact, building this lower dimensional projection. And so we apply the Johnson-Lindstein's lemma in the manifold version. And so we know that there exists some random ortho projection mapping points from capital D to D delta, right? And we can construct, in fact, a neural network achieving this type of projection, and I call it capital psi, which is defined internal of the ortho projection. Now, I can define, based on this ortho projection, a low dimensional function, which is, in fact, defined by identifying a function f measured at a certain point x, y, associated with my mapping to a function g in the g with value in the lower dimensional space. So I can just build this function for specific values, right, on which the mapping is defined. I can define my lower dimensional function. The point is actually it's not automated that this function is Hoelder continuous. And so a simple argument, relatively simple argument, shows that, in fact, the Hoelder continuity of my function g naught is a consequence of the Hoelder continuity of f and the Lipschitz property, the bi-Lipschitz property of the Johnson-Lindstein's map. And so this is going to show that my lower dimensional function g is also Hoelder continuous. The point is actually that at this point, this is only Hoelder continuous, not on the entire space, but only on the image of the map, right? So to continue the argument, I need to apply an extension argument to go from my function g initially defined on this image of the map to the entire space, to the entire domain 0, 1 to the d, which is done by an appropriate extension lemma. So this is actually the key part of the proof. Then the second part of the proof, which I will essentially skip, is that you need to build a proper neural network. And here we are relying in part of the work done by several people, including Petersen and Hoelder. I think that they gave a talk also in the Petersen may give a talk at the same seminar, showing that there is a whole machinery of building neural network by concatenation, parallelization. There are ways to approximate monomials and so on, which is the key, in fact, in achieving this type of approximations. And then once you have the appropriate construction neural network, then you can use this machinery to show that, in fact, you can realize the whole transformation I stated in the first part of the proof using, this type of neural network. Anyway, so after that, so once we have the approximation result, there is an interesting application which actually that we also found, which actually some observation about the generalization error, right? So the problem I consider here is the non-parametric regression problem, where you want, in fact, to approximate samples yi defined by a function f naught of xi with some noise. I assume, consistently with my general framework, that my function f is, again, a Hoelder function in a capital D dimensional space with some, with a bound, on the Hoelder constant. There are some technical assumptions I need to make on the noise. And the goal here, in fact, is actually to compute the regression solution, right? So the solution of the regression problem is an estimator that approximates the unknown function f naught, and the performance of the estimator is what is normally called the generalization error. So the L2 norm of the difference between the f and the estimator is measured through the expectation there, right? And what we're going to do in our case, we're going to identify the estimator class with, in fact, a class of ReLU neural networks. And results by other people, other investigators, have shown, in fact, that if this is what you try to do, in fact, you can estimate the generalization error in a way that depends on the sample size. And in fact, you will find, not surprisingly, that the generalization error depends on the sample size and scales with the ambient dimension capital D, right? And this is the optimal rate that you can achieve. So as you see, consistently with all other results, again, we get the scaling with the dimension and another form of the curse of dimensionality. So we will revisit the problem now using the manifold assumption. So we assume that the data that are in the ambient dimension capital D are, in fact, embedded lie on a lower dimensional manifold. And in this case, we are going to look for a regressor, right, which is actually defined on a manifold. And so we are going to look for a solution associated with the empirical risk minimization given here, where I'm going to look for a neural network phi defined through this, in a class of deep neural networks. And in this construction, in fact, I'm again exploiting the idea of, I'm still using the idea of projecting my data into a lower dimensional manifold through an ortho projection similar to the one I mentioned before, mapping my capital D dimensional data in this lower dimensional space where I use the effective dimension dE. So with this type of framework, we prove the following result, that if we look at a function f, which is Hoelder continuous with a bounded Hoelder constant, with support in a compact Riemannian D-dimensional manifold, then when we estimate the generalization error, we find that the generalization error, the bound for the generalization error, in fact, as you see in my estimate, will be controlled not by the capital D, but by the D sub E, right? Will depend not on the ambient dimension, but on vis-a-vis. But the main novelty is thanks to our new approximation result, the constant C, the multiplicative constant, again, will not depend on capital D, but only on the lower dimension, which is an improvement with respect to existing prior result, right? All right. So let me conclude. So the okay, I presented a contribution to the research on approximation property by neural network. And the argument that we use to derive this improved result is the use of the Johnson-Easthouse lemma in one specific form to claim the existence of a nearly isometric map from a higher dimensional space to a lower dimensional space. By using this type of approach, we do not need to explicitly construct a chart defining the mapping. So this will define some type of non-constructive argument. One drawback is actually that because we do not construct explicitly the map, and we need to use the this ortho projection, then in fact the projection is not on the dimension D of the manifold, but on a slightly on a higher dimensional value d sub b, which we call the effective dimension. So one question is actually whether one can derive a similar type of estimate constructively, mapping the data directly into D rather than D sub B. I also want to make a comment that the results I presented here, right, are all derived under the assumption that my approximators are in fact in the class of ReLU neural networks. If the activation function is chosen in a different class, the approximation properties are known to be very different. And in fact, I want to mention some group of recent results by Jarowski, who show that if you choose your activation function in a class which is called super expressive, then in fact you can achieve much higher, right, approximation property. In fact, you can show that there are fixed size networks which are with super expressive activation function. They can achieve continuous. They can in fact achieve arbitrary accuracy approximation without the need, in fact, to build this more complex architecture. However, you know, the use of this activation function may bring additional problems. Related to this topic, in fact, I also want to mention something called the study of implicit neural representation, which in fact somewhat exploit the same idea for a practical application, right? Anyway, thanks. This is all I wanted to mention. So the result I presented is more or less contained in a paper that we actually published very recently in neural networks with, I mentioned my student G, and to G goes all the credit for, you know, the clever ideas in the paper. Thank you. Please, I see some hands. So
sorry, everyone smash that reaction button. And then if Dustin wants to stop the recording.